Yeah. I kind of struggled with the title of my talk. The next slide I get, even on the websites, I think it still says TBD. I put this, but it's not really this. Really, it's like using transducers as a tool to like really kind of poke around and have fun with functional programming. And really, this is just a verbal version of a playground HTML file I made and put up describing what transducers are, and like, I don't know, it's kind of really fun in a playground to be able to like tweak values, poke at things, and describe how these things fit together. So we're gonna do some playground stuff too. So this is all, me going last means like everything I'm about to say has been said so many times now, except for maybe the first one. It's been mentioned, but I'm gonna like really poke at it a lot. So function composition. Rule number 0, the most important thing, a functional language would not be functional, in my opinion, if composition was just natural, flexible, promoted, the most important thing. Immutability, statelessness, we've talked about that so many times now, maybe I don't even really need to say anything. So function composition. This first bullet point, not totally correct, but we'll see in a playground why I don't consider them to be composable. Although I liked what Andy said about using a static method on a struct in order to like maybe put some object-oriented people at ease, because at least it's inside something. But everything I'm gonna do is gonna be free functions, and it's gonna be a good life. And yeah, we should just be doing everything we can do to make composition better, and curried functions are highly composable. And just like Natasha said, in Haskell, indeed, everything is just curried. Every function takes one argument, and that's pretty nice. So we get our first playground. This is kind of scary for me. Two things scared me about this talk. One, live coding in a playground, and having the same deck set theme as someone else. But I chose the most basic deck set theme, so. All right, here we go. Oh yeah, maybe I can just do that. Yeah, that's better. Let me kill this guy. All right, so we're gonna talk about, oh, this is gonna be so weird. I'm gonna turn a little bit. So why would I say methods are not super composable? I think I have something, here we go. Look at this guy. So these, I've extended int, which is a struct, and added some very basic functions. And you can use them quite simply. I can, oh, uh-oh. Why would that? Oh, you know what? Whoa. Sorry. I was making a last second change here, and sorry. Let me, Okay. Still not sure what's going on, but maybe completion isn't going to work, but all right. All right, so this is how we would normally use a method. It works. Oh, I should go back to big. That's good. And what methods give us, oh, there we go. Methods give us chaining, and that's basically composition. But here's where things break down. I wanna be able to have an array of x's. I'm gonna take 100 of them, and then I want to do things like map on them, and I want to map with square. Square lives inside this int struct, and Swift does something really great, which it gives you access to this static method, but it does it maybe in a weird way, and I'm sure there's probably a great reason for it, and I just don't know, and so if someone, I'm sure it's really good. But you can see, if I plug something into this square, I'm not getting the square of the integer, I'm getting the function, which, what is going on? Why is this acting so crazy? I think I am actually going to do that. So sorry. Hmm. I'm so sorry. Yeah, I'm sorry. Yeah. All right, so yeah, so the thing I want to show here is that plugging in 3 doesn't actually give us the square 3. It gives us the function which does nothing but return, like it kind of wraps it in a closure. So this is weird. So basically, this thing has the signature of an int. It has something like this, really. And we could easily write like a function that would collapse that inner empty tuple. And I've been trying to think of a name for it. I think it would be called unit because I think it's kind of like what might be the unit in something called a monoidal category, but I'm not going to go there. So I don't know. This just is not a reusable thing. So we're going to go full free function and redefine those. Oh, you know what? My notes here are telling me that I don't even have to do that. There they are. Now we can map our x's with square. And now we're sitting good. That's nice. And then the other part was promoting composition. We should do things. Swift allows us to find new ways to promote composition in ways that maybe Swift doesn't do natively, but that maybe we want to do. I'm going to define some operators. These guys here. I only put the signature. The first line here is just Swift needing to say, I'm defining a custom operator. What does this operator do? It takes something in A and a function that goes from A to B, and it spits out a B. Now, here's our first example of the compiler basically writing code for us. There is absolutely nothing I can do except stick that X right into F. There's just nothing I can do. It is just a universal law happening here. The next one is just a little bit more complicated, but now instead of an X, we have an F from A to B and a G from B to C. How do we get something from A to C? Again, the compiler is basically writing it for us. We need to return a function from A to C, so we have no choice but to return something. That is this piece here. So it's a closure, a function that would take an A, so we can just call it A. Type inference has already figured out what it should be. Now we have an A, we have an F, we have a G. There's just nothing we can do but plug A into F and then plug the result into G. There's nothing else. We know nothing about A, B, and C. It's very nice. And now these operators allow us to kind of change some of the things we were doing. Now I can pipe 3 into square, and then I could pipe the result of that into increment. That's cool, but nothing really new. The really cool thing is I can take my x's. Oh, wait, no, I can't do that yet. So I can also change like the order of parentheses. The left associativity means all the parentheses are heavy on the left, but instead I could just pipe square into increment. And then now 3 is being piped into the composition of square then increment. So back to composability, map. This is the signature for map in the standard library. And this is just so wrong. But it's very familiar, so maybe it's not so wrong. But really, how can we enhance composability with this? Going back to currying functions, every function not should take one parameter, but when you have that property, you're in a really good world. So I'm going to redefine map. I need 2 generic parameters, and in fact, no, I don't think. And what does it want to do? I'm going to basically just switch the order of these things. I want the transform to come first, and then I want to return a function that goes from array of A's to array of B's. So now a map, it's not give it a source, give it a transformer, and we do the transformer on the source. Now it's give me a function, and I lift it from the world of A to B up to the world of array of A's, array of B's. And I'm just going to give it, I'm not going to actually, like, and then inside here, I don't care now. I'm going to use the regular map. Now what can I do? Now I can do good stuff. Now I'm going to pipe my x's. I can't pipe it into square. Square takes a single integer. Map lifts square from the world of integer to integer to array of integers and array of integers. So now I lift square, then I can pipe it in. Then I could pipe it into increment. Or I could just remove these guys. Now I'm piping the x's into the lifted composition of squares and incremented. Cool, super cool. Also, the difference between these two things also is that the first one, line 52, I'm iterating over the x's twice, and the second one, I'm only iterating once. There's one function that I've lifted up to the world of arrays, and I apply it to the x's. So real quick, I'm also going to do the same thing for filter, because we're going to use that later. Filter, the standard library filter, again, did it wrong. I mean, not wrong, but for this talk, a little bit wrong. So again, the source and then the predicate. I'm going to flip it and curry it. So filter is going to take the predicate and then lift a predicate up into the world of arrays. And I'm just going to do the basic thing. I'm just going to now call out x's predicate. All right, so I prepared a really nice predicate, which I was not going to live type somewhere, is prime. I mean, it's kind of a messy implementation, but this is stupid. It just, you only need a loop up to the square root of a number in order to check for prime factors, so it just does that a little bit more efficient. But I wanted that guy sitting there, because now what I could do is I might even have this in my pasteboard, yeah. Then I could pipe that into is prime. Now I've got all integers of the form x squared plus 1, or n squared plus 1, that are prime, where n ranges from 1 to 100. Those are them. Those are all prime, and they're of the form n squared plus 1. Now I'm iterating over the x's 3 times to square them, to increment them, to filter them. I could reduce it 1 time with this guy. Now I'm iterating twice. But we stop there. Filter its signature is just incompatible with mapping. There's really nothing we can do now to enhance, to compose this any further. And really, I mean, we could just write it from scratch that just iterates over these things, squares them, adds them, check its prime, but we're not reusing these nice little atomic units of functions we have. So that is what, oh, that's a summary of what we just did. And this is good. It's good because it's readable, it's modeled on the flow of data, and it's expressing what we want to compute, not the messy details of how we want to compute it. It's bad because it's inefficient, and someone was talking about that earlier. And even simplifying it isn't good enough. So transducers want to fix this. It makes all of these little array operations highly composable. So you don't have to break out of the framework of the nice little atomic unit functions you have and want to map them and filter them. You don't have to write like a custom hodgepodge of taking those in and make a custom n squared plus 1 prime filter. You get to actually just use those pieces. And in the process, I mean, already that's good enough. We've now made a better composable program, but you also somehow also reduce even the number of traversals. So good stuff all around happening. And it all is from this really nice idea that reduce or fold or whatever you want to call it, it is very universal in the world of operations that happen on arrays. Every little thing you might want to do on an array could just be rewritten in terms of reduce. There's a very beautiful idea. It's heavily embedded in the world of category theory, but I'm actually more of a mathematician. I went to grad school for math and everything, and so category theory is very natural for me. So this I find very beautiful. If you look up the Wikipedia, it might seem absolutely awful, but and so I just have like a little demo of that. Let's see what we find behind door number 2. There we go. This is me rewriting map in terms of reduce, filter in terms of reduce, take, where you give it an integer, and you just take like the first 2 or first 100, and flatten in terms of reduce. Everything is reduce. That's pretty cool. So using this idea, maybe we take all these maps, all these filters, and there's tons of them. You look up the list package in Haskell, and you'll find tons of things. Or maybe if you know Ruby, there's the enumerable module. It's just a list of things that you do on enumerable type things. All of those things, rewritten in terms of reduce, maybe we can get ourselves into a world that's more composable. Because if everything is reduced, maybe somehow these things all fit together. And it totally works out. So a term, a reducer is just a function, the line broke, but it's C comma A to A. Just something of that shape. If you see that shape, that's all a reducer is. So nothing too technical. And then transducer would be something that takes a reducer and spits out a reducer. That's all it is. But let's actually see that. Okay. I actually wrote out a very simple transducer. It's called squaring. It takes any reducer on integers and spits out a new reducer on integers. And all it does, and in fact, yeah, so it needs to return a new reducer. I'm going to call the first argument the accumulation, and that kind of makes sense when you are reducing on arrays, because sometimes you're accumulating values. You're either summing or appending objects. So this right here is the shape of this. And inside, I'm just going to, again, I really don't have a lot of choices of what I can do here. I need to plug in something of type C. The only thing that I have of type C is this accumulation variable. And then here is where I get to be fancy. I want to do like a squaring thing. So here I've squared x. How do you use that? So this is even this exact example was in Natasha's slides. This is how you might produce the sum of those x's that I defined way, way above. What if I wanted to sum their square? I can just lift my reducer plus up into the world of transducers, and now it's mapped the plus reducer into the plus of squares reducer. Okay, that's all that is. So that's an example of a reducer. Okay, and that's just exactly what I did. All right, but we're going to generalize that. Over here, the squaring reducer did x times x, but anything could go there. I can do whatever I want to those x's. So that's what we'll call mapping. Mapping lifts a function from A to B up into the world of reducers. And then something very subtle here, but there's a very well understood reason why, and it's very tricky, but once you get it forever. But the reducers, the arrows switch directions. It's going from a reducer on B to a reducer on A. F went from A to B, but the transducer goes from B to A. It's okay. And in fact, the type system will often just like let you know, unless A and B are identical, the type system would even tell you you're doing something wrong. But it's a very subtle thing, and if you want to look into it, it's called contravariance. And then I could also do a filtering transducer, which lifts a predicate up into the world of transducers from A to A. Oh yeah, I'm sorry. Oh, you know, I wanted to go back to the playground because I wanted to actually I wanted to implement this because it's another good example of the compiler forcing you to write things until it's okay. And you really have no choice but to write what it wants you to write. So what do I want to return? My mouse keeps. I want to return something that takes reducers and spits out reducers. So I'm forced to return something like this, and it's going to be a reducer. It's going to be a reducer on B. All right, so I have a reducer on B. Now I need to return a reducer on A, something of this form. So reducers are functions. I got to open up another closure. But this reducer takes an accumulation and then something in A, something we're reducing over. All right, Now I'm finally need to produce something in C. I have something in C, I have something in A, I have a reducer on B. I really cannot do anything but what I'm about to type. I can, well, first of all, I can apply F to A. Now, compiler's not gonna be happy with that because that puts me in B, not C. But now I have something in B. Reducer is a reducer on B, which means I can feed it that B value and the accumulation, and now the compiler's happy. This is all this could be. It can't be anything else. Very nice. And I hope that filter is okay, good. So I'm not gonna write this one, but it's basically what you'd expect it to be. All right. So how do we use? Well, we got to feed it reducers. Transducers want to be fed reducers. A really good reducer on arrays is append. I wrote it as a free function, and one that returns a whole new array, not mutates. So I don't know why I comment. Yeah. So I'm gonna put that guy back in, and see how we can redo that prime example where I squared integers, I added one, and then I filtered by prime. So, okay. Well, I need to reduce because I have transducers which map reducers to reducers. The sequence I need to put in is the x's. The initial value, well, I want to create a whole new array. So the thing I'm accumulating with is an array. I can even leave off the type because the type inference will figure it out. That's nice. I can throw in, like, let's say I do mapping square. Before I did map square, this is mapping square. This is a transducer. I can't feed it into reduce. You can only feed reducers into reduce. So transducers take reducers, spit out reducers. I need to feed it a reducer. All right, that should give me, okay. All right, so that only took care of the squaring situation. Then I needed to increment, and this is where the arrows flip direction, and now I actually have to put increment first because of the contravariance. And now this will be the n squared plus 1s of my array. Okay. Now I need to filter the primes. Okay, I've got filtering, and I can give it is prime. And let's see what that does. Called way fewer times. The append only happened 19. This array only has 19 elements. And there's only a single reduce, which means there's only one traversal. Yeah, that's pretty good. Then what if I wanted to not just find all those primes, but instead sum them all up? Super easy. Now I want to reduce on 0, and I want to use that plus reducer. Yeah. So highly composable, reusable, atomic units of functions. These functions are pure. And then on top of that, if I search for the keyword let, I'm going to search for let. This is the only place, in order for me to say I had an array of x's. Nowhere in the entire, it is a fully stateless thing I've been doing this entire time. And that's kind of nice. So yeah, that's mostly it, but I think a good exercise is to figure out how to lift other collection functions up into the world. There's take, you could call it taking. There is until, I don't know what to call that, but until basically concatenates elements until a predicate is false and then it completely stops. But yeah, it's kind of nice exercise and like basically matching up types to do what you want. I think maybe, let's see. Oh, yeah. And that's looking really nice. So what's missing? All right. It would be very nice if you could deal with transducers abstractly. And this is exactly what you can't even do with monads that John was talking about. You can't have a monad type, you can't have a transducer type and say, I abstractly have a transducer from A to B and then deal with it. Because if you could, well, not because if you could, but if you could, and you had a transducer from A to B and a transducer from B to C, you could create this piping thing to create now a transducer from A to C. Like, it would be very nice to be able to write code that just could abstractly deal with these things. You can't. You can get kind of close, but you still can't really get all the way there. It's just the type system just isn't power enough right now. That's okay, because in the playground we saw we got pretty far. We just, yeah, you just can't really do some cool things. And oh yeah, I think that's the end. Questions? Yeah.
One of the authors of the lens library in Haskell proposed that lenses are just transducers and reducers with types.
Dude, yeah, totally. I mean, so I wanted to open this with, like exactly the weird circus that this entire transducer movement opened with, and how it really, it's just a nice idea. I love using it as a method to kind of poke at functional ideas and to lead us through this thing. But yeah, if you've got a good enough type system, like, you can actually go far and above this, and this might just be a special case of something far more general. But yeah, totally good point. Any other questions?
One thing is the best name I've heard for somebody killed that thing that turns a method.
I'm sorry, I can't hear.
The best thing that I've heard somebody call that function you need to turn a method into a free function is dismember. But, on the forums recently, I think Chris Latner said that their preference is to go all for methods, that they want to do all around that sort of thing. And I wonder whether that's going to mess up this kind of technique, or whether that's taking switch.
Oh, I'm sorry. So Chris Latner said not to do free function.
Well, no, they in their thinking are trying to favor methods.
Yeah.
And do things like give methods the ability to have restrictions on the type, the struct, and things like that.
Yeah, I think they're completely equivalent, because even that weird int to unit to int signature we had, you could always wrap that in some function that removes that middle step. So they're absolutely equivalent. I just find it weird that I need to, and I feel like a really good point's about to come. I just feel like it's unnecessary to wrap that, and now.
It is unnecessary. The only reason there are free functions, like they do want them all to be methods. The only reason there are free functions is that you can't implement methods on protocols.
Right, okay. Yeah. Yeah, very good points. Way in the back.
So there's one point I was trying to make sure I understood. So basically, you reduce the number of you reduce how many times you iterate over the data set by the transducer passing the function along to the reducer. Is that essentially what you did? So in a way, maybe lazily evaluating?
Yeah, not really true. It's a little bit separated from lazy evaluation. The transducer is allowing me to lift, map, filter, take, until all those things into a single world where they can all be composed. And that's all. That way you can compose it into one master reducer. And in fact, this right here is just one massive composed reducer that is fed into reduce, rather than reducing multiple times for each one or mapping multiple times for each one.
And you can pull it into a variable.
Yeah, totally. I could call it the master reducer. Whoa. What was? Oh. Yeah. So, yeah. Yeah.
So I got a little bit lost earlier, but you said there was a thing that was a reducer from A to B, and it took in a reducer of A to B, and it returned a reducer of A to B. Mm-hmm. So in my mind, I was thinking that's an identity. couldn't that just return?
Okay, so maybe what you were talking about was it this slide where I've got a function from A to B, and I lift it to be a transducer from B to A?
No, I think it was one before that.
Okay, so then,
This one.
yeah?
Yeah, so it takes a reducer of what is it called?
So it would have been the identity had I not squared it, but here I decided to create a squaring transducer, and yeah, I squared in there. But had I put X in there, it would have been the identity reducer. And mapping just allows me to generalize that for there to be any transformation in this piece here.